Sorry for that rather abrupt ending of the last video. My fat finger hit the stop record button before I meant to. So what we're trying to do, we're still working on that same example that we were at the end of the last video. We're dealing with this function g of x. We found its inverse. Its inverse is negative 1/4 x plus 3 halves. And we want to identify the domain and the range of the inverse. So just like before, you could go ahead and graph this inverse relation. You want to figure out if there are any values of x that we can't have. In this case, since we're still dealing with a linear equation, the domain once again is all real numbers, as is the range, because again we're dealing with a line here. And then we also want to determine whether or not our inverse of g inverse is a function or not. And since this equation here is just simply a linear equation, then yes, it is. If we graphed it, you could see that it would pass the vertical line test. Probably should have picked out a slightly more interesting function in its inverse. But it does turn out, even though it seems like the domain and the range just happen to both be all real numbers, and that's not all that exciting, it does turn out that the relationship between a function and its inverse, because we're switching the x and the y values, that also switches the domain and the range of the two. So for instance, if a value was excluded from the domain in your original function, that same value would be excluded from the range in your inverse function. Okay, I know we've gone over quite a few things so far in the first part of this video, but we've got one more topic that we need to discuss. And I said initially, when I introduced the topic, that we were going to bring the idea of composition of functions and inverse functions together, and here it is. So, by definition, if f, some function f and its inverse, f inverse, if they are truly inverses of each other, then when you take the compositions f inverse of f of x and the composition f of f inverse of x, in both cases you must get out only x. That is the only way that two relationships that you're looking at can be proven algebraically to be inverses. If when you take one and compose it with the other, you get x out as your final result. The reason that this composition of a function and its inverse prove that they are inverses when you get x out at the end is because it literally is saying whatever the function does to x, the inverse of that function undoes. It sort of reverses everything that you're doing to x. So this probably sounds a little abstract, so we're going to do an example. Alright, so we want to determine whether this function f of x, which is 5 times the cube root of x plus 4, and the function g of x, which is x over 5 cubed minus 4, we want to determine whether f and g are inverses of each other. So that means we need to evaluate two different compositions. We need to evaluate f of g of x, and we also need to evaluate g of f of x. Our two functions, f and g, are inverses only if, when we evaluate the two compositions, we get x out in the end. So that's what we're going to do on the next slide. Let's do f of g of x first. So if we're going to evaluate f of g of x, that means that since g is on the inside, that's where we start. So we're going to plug in our function definition for g, which is x over 5 cubed minus 4. And we are plugging that entire value into our function f. So we need, wherever we see x in f, we're going to instead plug in the expression x over 5 cubed minus 4. Now our function f is 5 times the cube root of x plus 4. So instead of x, I'm going to do x over 5 cubed minus 4. Put that in brackets. And then plus 4. So now we just need to simplify this. Well, we can start off by combining negative 4 plus 4. That's 0, of course. So that means our right side of the equation simplifies down to 5 times the cube root of x over 5 cubed. And we know that a cube root and the cube function, those are inverses of each other, so those are going to undo one another. So that means we're left with 5 over x over 5, or 5 times x over 5, and of course the 5's cancel, leaving us just with x. So this is a good indication that f and g are most likely inverses, but we're not quite finished because we need to evaluate the composition in the other direction. So we also need to evaluate g of f of x. So this time, since f is on the inside, we're going to plug that in first. So we're going to plug in 5 times the cube root of x plus 4. And now when we go back to our function definition for g, every time we see an x, we're going to plug in this expression 5 times the cube root of x plus 4 in for x instead. And of course g was x over 5 cubed minus 4. So instead of that x, we plug in 5 times the cube root of x plus 4. Then we're going to be dividing that by 5. Then we have to cube the whole thing, and then we are subtracting 4. Let's make sure I wrote down everything correctly. Yes. Okay, so now we just need to simplify as much as possible. So of course we start off by canceling out our 5's. That leaves us with the cube root of x plus 4 cubed minus 4. The cube root and the cubic function cancel each other out, so that leaves us with x plus 4 minus 4. And then, of course, 4 minus 4 is 0, so we're just left with x again. So that means that because both g of f of x equaled x, that was the result that we wanted here, and f of g of x equaled x, that proves to us that our original functions f and g are in fact inverses of each other. If when we had done this composition in either direction we had ended up with something other than x as our result, say maybe we ended up with x minus 1, or we ended up with 3x or something like that, then that would tell us that our two functions f and g would not be inverses of each other. You have to get just x out at the end to prove that what one function does, the other function reverses. Alright, I think I've thrown enough your way. I apologize that these videos were so long, but just take your time with them. If you need to watch them a couple times, you've got all weekend to do it. See you Monday.